start. Welcome everybody to the webinar of today. The speaker of today is Luca Brandt, and he's going to talk about modulation of homogeneous and isotropic turbulence in emulsions, energy fluxes, and droplet size distribution. So as usual, I introduce the speaker and then very briefly, and then I leave him the floor. So Luca Brandt is Professor of Fluid Mechanics at the Royal Institute of Technology, KTH, Stockholm in Sweden since 2012, and at the Department of Energy and Process Engineering, NTNU, Trondheim, Norway since 2021. He received a Master in Mechanical Engineering from University of Rome, La Sapienza in 1997, and a PhD in Fluid Mechanics at KTH in 2003. Before joining KTH as an assistant professor, he spent several months at École Polytechnique in France and at the University of Bologna in Italy. Luca's research interests are in general area of multiphase turbulence, particulate and flows, heat and mass transfer, low Reynolds number flows, and complex fluids, hydrodynamic instabilities, and flow control, with a focus on the development of theoretical models and high-fidelity numerical simulations. He has more than 180 peer-reviewed journal papers, including one annual review of fluid mechanics in 2022. He was the recipient of an ERC Consolidator grant to study particle suspensions in 2013, and of the Outstanding Young Researcher Award from the Swedish Research Council in 2014. He had been awarded of the Gustafsson Prize in 2005, and the position of as Outstanding Researcher in Mechanics by the Swedish Research Council in 2008. Luca has served the community, organizing several workshops and summer schools, and he's associated editor of European Journal of Mechanics B and of Mechanica. So it's with great pleasure that I introduce Luca Brandt for the webinar of today. So Luca, I stop sharing my screen, and you can start sharing yours.
Okay, can you see it?
Yeah.
Okay, so thank you very much. Thank you very much for inviting me to this seminar. Also, thank you for organizing this nice series. I was looking at how many seminars you have now on the YouTube channels with really many visions. So I'm happy to be here, and I will present today the work. And let's say I will talk about one single thing today. Maybe I will focus on this recent work I did with in collaboration with Marco Crealesi, Esposito, who was a postdoc at KTH, is now a postdoc in Torino at the ENFM. And Marco Rosti, who was previously at KTH, and now is professor in Okinawa, in Japan. And then also Sergio Kibaro from France, is professor at LMFL. So what I will talk about is, as you mentioned, modulation of homogeneous isotropic turbulence in emulsions. I will look at and I will do an energy flux analysis, and then I will try to relate this to the droplet size distribution. So, oops, yes, okay. So, of course, emulsions are important for many different industrial applications. Here is mayonnaise, but also, of course, can be important for geophysical flows and natural phenomena. But what we want to do here is something a little bit more fundamental. It's more like a fundamental study of multiphase turbulence. And so emulsions are nice because they allow us to study multiphase flow turbulence in a simple configuration, where we can focus on the effect of the form of a interface. So we have basically a certain number of droplets and dispersed in the flow. And of course, one of the objectives here then is to try to relate the droplet size distribution to the characteristics of the turbulence. We will assume even simple configuration. We will assume homogeneous isotropic turbulence. And this is because so we can more easily compare to single phase turbulence and try to understand the modulation of turbulence and how the turbulence cascade is altered by the presence of these droplets. Then, of course, the work here is mainly based on simulations. And of course, trying to simulation, we can try to understand disentangle the role of viscosity contrast, volume fraction, surface tension separately, and also, of course, density ratio, although this is something we are doing now and this therefore not discussed here. So the main question, at least for this first part of the talk, would be how are the flow properties modulated by the presence of an interface, and how is the classic scenario of homogeneous isotropic turbulence modified in the presence of the droplets. As I said, this work will be based on numerical simulations. So what we'll do here, we'll solve the one fluid formulation and Navier-Stokes equation for a mixture of two incompressible fluids. And these are now the Navier-Stokes equations, where we have this forcing term here, which is just added to sustain the turbulence. And this is the forces due to the presence of the interface, where xi is the curvature, sigma is the surface tension coefficient. And then this delta localizes, of course, the forces at the interface, at least in a numerical sense, and n is the normal to the interface. What we do, we will use our volume of fluid implementation of the M-think method, which was first suggested by E and co-workers in 2012, it's a Japanese group. And then we have a paper here with different validations and more details on the implementation. When it comes to the forcing, then we sustain as homogeneous isotropic turbulence, and we do that with this ABC forcing, classical forcing. Okay, this is just a movie to give you an idea of what kind of simulation we have done. We have a triperiodic box, size 2 pi. The resolution is 512 grid points in each direction. And the forcing now is the forcing we have mentioned before, the ABC forcing sustaining turbulence, is on the second wave number. And this has been shown in previous works, for example, Perlecar and others, that this, from a numerical point of view, avoids the formation of large bubbles or droplets. So try to a little bit minimize coalescence and the effect of the periodicity of the boundary conditions. The simulation are performed on this single phase turbulent field with a relatively high Reynolds lambda, 137, at least relatively high for multiphase turbulence. And then what we will do in simulation, we will vary the volume fraction of the dispersed phase from 3 to 50%. So half, then basically is binary mixture. And this we will do for viscosity ratio 1, so same viscosity of the two fluids, and the Weber number based on the large scale, which is 42. Then we will look at the effect of Weber number. I said it doesn't mean too much if I just introduce like this, but we will see then the effect of Weber number. We'll also study a variation of viscosity ratio from 0.01 to 100. And this we do at a fixed volume fraction of 10%. And then we will vary also the large scale Weber number, which is based on the L is the box size, the UMS is basically the intensity of the turbulence, and sigma surface tension coefficient. And we will vary it by 1 order of magnitude. For at least for this case with 3% volume fraction. Now, if I go to the next slide, we will of course do the simulation. We can extract different features from the flow, but the idea here also is to study multi-phase flow, this an emulsion where coalescence and breakup are present, and to try to extract information in statistical sense. So what we will do, of course, look at usual global measures of turbulence, like Reynolds lambda, the turbulent and production, dissipation, and so on. But in particular, we'll focus on the scale-by-scale energy balance. We look at the energy budget at the different scales. And this, I mean, we can obtain directly, starting from the Navier-Stokes equation, which I mentioned earlier. If you just take Fourier transform that will go into the spectral space, we will have something like this. We can then multiply by the complex conjugate of this equation. And then we have an equation for the evolution of the kinetic energy of the flow at scale at a certain wave number ki, where this, of course, is now a three-periodic box. So we have homogeneous isotropic conditions. And what are the different terms that appear in this scale-by-scale energy balance? Of course, we have the time derivative of the kinetic energy. T is the energy transfer due to the nonlinear terms, the convective term and the Navier-Stokes equations. Because of, also we assume constant density, there is no density contrast in this result. Then we will have the pressure force can be easily eliminated. Then we'll have D, which is viscous dissipation. Then we'll have S, what we call S of sigma, which is basically the work from the surface tension forces. So the contribution from the surface tension forces at the specific wave number. And then we have F, which is the energy input due to this large scale ABC force in a sustained turbulence. So we will look at these energy terms, in this energy balance at each wave number. Now, just to give an idea of what this term implies, what we may recall is that, of course, if we integrate over all wave numbers, then we get the more or less classic turbulent kinetic energy budget, sticky budget, where we have raw time derivative of the turbulent kinetic energy is equal to production term minus dissipation plus, if we will have a term psi of sigma, which is the integral from the work of the surface tension forces. Now, we sustain turbulence because we want to reach statistically steady conditions. So this time derivative will be zero. Also, is known that the nonlinear terms of the Navier-Stokes equation just distribute energy through different scales. So the integral net contribution to the TKE budget will be zero. But then it's also important to mention here, oops, I cannot, oh yes, that when averaging in time, if I do a time average, at steady condition, also the total net contribution from the surface tension forces will be equal to zero. This is nicely demonstrated in the appendix of this paper, where the authors show that the total contribution from the surface tension forces, what we call psi or sigma, is proportional to the time derivative of the total surface area, so the total interfacial area between the two faces. And this, in steady conditions, statistical steady condition is approximately zero. So we expect, from this analysis, this term also to be zero. So that eventually what we have is that P is equal to epsilon. But of course, what we are more interested in is the possibility to look at the contribution of these different terms to the different terms I mentioned before here, of these different terms to the total energy in the flow, and to relate this, of course, to the to two things: to relate this energy spectra to the case of single phase to see how this is modified, but also, of course, we want to relate this to the droplet dynamics and droplet size distribution. That will be basically the second part of the presentation. Okay, these I've shown. So let's start now with the results of these simulations. We start with some global measures, and we start then with Reynolds lambda, classic Reynolds number, which I like to think of as the ratio between the largest and the smallest scales in the flow. This is basically, here we have K, the turbulent kinetic energy. Lambda is this Taylor length scales, which relates dissipation, turbulent kinetic energy, and viscosity. And then, of course, Ni is the kinematic viscosity. So these are now the results, Reynolds lambda versus this integral length scale lambda for the different parametric studies we performed. So here we have results for increasing value of alphas, for increasing values of alpha, or the volume fraction. So we see that we have an increase of Reynolds lambda, so in some sense an increase of the turbulence with the volume fraction. And we also see that increasing alpha, the increase of Reynolds lambda is proportional to lambda. So not directly related to the variation of K are more or less negligible. All the increase in Reynolds lambda can be related to the increase of lambda. And this can also be related, be proportional to the total surface area, right? We see that the effect is proportional to the total interfacial area. Then in this plot, what we do is we change now the viscosity ratio. So this is for low viscosity in the dispersed phase, and this is high viscosity in the dispersed phase. And we see a significant decrease of Reynolds lambda when I increase the viscosity ratio. So with low viscosity in the dispersed phase, we have a significant increase of the turbulence intensity. And this is now variation with the Weber number. This is high Weber number, so lower in surface tension, and this will be a stronger surface tension. And we can see that in general, if you have a more rigid, either more viscous or stronger surface tension, rigid dispersed phase, then we have, if the dispersed phase is more rigid, then we see that turbulence is kind of quenched, is damped, is reduced in intensity. Okay, oops, that's the next one. Now, if we, now what we're seeing here, in any case, with the increase of Reynolds lambda, so the Taylor Reynolds number can be related to the increase of the length scale lambda, which is defined as proportional to the ratio between the kinetic energy and the dissipation. And so we try to understand this. So these are basically planes, some randomly chosen planes for single phase and two-phase flows, where I plot here lambda, the logarithm of K over epsilon, basically, and below instead what I plot is only the dissipation epsilon. So what we can see here from this plot, we can see that the dissipation, the total dissipation, the energy dissipation is more or less constant. It's not changing too much. And as I mentioned before, this is equal to production because surface tension effect is 0 on average if I integrate over all wave numbers. So we see that total dissipation, we can see it is more or less constant. But if I compare these two figures, I can see that there is an increase, that there are region of intense epsilon, intense dissipation, localized region of intense dissipation, which are more obvious in the multiphase flow case. Now, you may not see this directly from these plots, but there are statistics to confirm this. What is interesting to see in the plot is that this intense region with strong dissipation, which you see, for example, here, are localized near the interface. So this seems to be a key effect. Now, if I look at the lambda, which is the ratio K of epsilon, we can see that turbulent kinetic energy, as I mentioned before, is less affected by the presence of the interface. It's more or less uniform and also in intensity. That means that if I take the ratio between K over epsilon, I have that I have an average increase of the mean value, because of course I have more instances where K over epsilon becomes very large. So I have an increase in lambda, which is not due to an increase of K or epsilon separately, but it's due to an increase of the ratio, because I can identify regions where epsilon can become very intense, a region where instead epsilon is almost 0, very quiet, like here. So this will correspond to an average increase of the K over epsilon or lambda. Now, if I go back to the statistics, I go back to the average quantities, then we can look here at the one-dimensional energy spectra in homogeneous turbulence. And this is now, these are now the results when I change the volume fraction, changing the viscosity contrast, and changing the Weber number. And we see that in all cases, we have a decrease of the energy at large scales. So the energy content goes down at large scales. Not here is maybe less evident. Here is more obvious when increase alpha. On the other hand, we have also a significant increase of the energy at small scales. And this is common to all the cases, whatever I change. And now we can also note, and we'll get back to this, that for all cases, the Hinze scale, which I will talk more about later, which is the scale below which, so on the right of this vertical line, which is the Inscale, what we have droplets that are too small to be broken by the turbulence, right? So it seems that the Inscale seems to describe quite well this pivoting point. So the transition from the region where energy is actually decreased and where energy is increasing. Then if I compare different plot, I can also see that the variation of viscosity, especially when the viscosity of the dispersed phase is lower than the one of the carrier phase, is the one providing the most obvious and visible variations of the spectrum. Oops, next one. Now let's look at the scale by scale budget that I introduced before. If you remember the different terms, and nonlinear transport, dissipation, forcing, and then the work of the surface tension. Now, to start with, let's look at what happens in single phase homogeneous isotropic turbulence at a relatively large Reynolds lambda 137, relatively large for simulations of multiphase flows, but where there is maybe the separation scale is not so obvious. What you can see here is this is a forcing term. Of course, I introduce energy at this second point. Remember, the forcing was not at the first, it was at the second wave number in spectral space, and I see this peak here where I introduce energy and then zero everywhere else. That's the only point where I inject energy. The red is the transfer of energy by nonlinear terms. I see energy which is transferred, so it's positive contribution. Energy is transferred towards the smaller scale, large values of the wave number k. And then I have this blue line, which is the viscous dissipation, which compensates basically for the transport here in steady condition. And then here I have basically laminar flows. I have sub-Kolmogorov here. Now, if I look at the same budget in multiphase flow, then we see that there is one extra term. That's what we want to study, is the work by surface tension. And what we see is now in black, the surface tension work, we see that surface tension is negative, as a negative contribution to total budget up to this wave number, which then becomes positive. So surface tension absorbs energy at large scales and then injects energy at these smaller scales. And this is a feature that we'll see for all cases. So as also shown in other studies, in previous study, like for example, Perlekar and his group in India, surface tension provides an alternative way to transfer energy from the large scale, which is absorbed, to the small scale where it's released. Yeah. Now, another thing I want to point out here is that energy is transported by surface tension well into the dissipative range. You see that the range over which there is significant dissipation is increased when I go from single phase to multi-phase flow. So that means that dissipation now is acting on scales which are smaller than the scales that where dissipation was active in the case of single phase turbulence. So we have an extension of this dissipative range, which of course, from a simulation point of view, implies that higher resolution will be needed if you want to correctly resolve dissipation and dissipative range in multi-phase simulations. Okay, now this is, I just look at the different terms of the budgets and how they change with the volume fraction alpha. We can see generally that as alpha increases, the interfacial areas increases, so the energy transport to the surface tension increases. So that's this term gets increasing with alpha. There is no significant difference in the shape, just an increase with the surface area sigma, with the surface area with alpha. Now we see the nonlinear term. Also, we see that as we increase the dispersed phase, the transfer from the linear terms decreases from the black to the yellow here. As I said, this confirms the fact that now energy is transported to small scales also by the surface tension forces. And then we see that, again, we see here in detail that as we increase alpha, as we increase the number of these dispersed droplets or the volume of the dispersed phase, we see that we have energy, significant energy, which is dissipated at smaller and smaller scales. Okay, this is now the same. Now we look at the three different contributions, now changing the viscosity ratio. And what we see is that if you have viscosity in the dispersed phase, we have a reduction in turbulence, and there is also a reduction of the activity at small scales. So when I have the dispersed phase, so the green line with the viscosity, which is 100 times the one of the carrier phase, I have that basically the viscous dissipation acts on scales which are similar to those of the single phase turbulence, and there is not this extension to a smaller scales. You see at the work of the surface tension, again, negative at large scale, positive at small scales. But what you can notice also is that this coalescence, increased coalescence, the fact that droplets have larger size, and we'll discuss the size later, but now for the moment, believe it. So since you have larger droplets, this shifts the peak of positive sigma of positive work towards large scales. So if I have largest droplet, the contribution of the energy moved to smaller scale starts for larger values of K. And then if I change now the surface tension coefficient to the Weber number, we see that despite this order 10 variation in the surface tension, the energy transported by the surface tension term doesn't change significantly. This is a fixed volume fraction. So the more effect is observed when changing the volume fraction rather than the Weber number. But when we change the Weber number, we change basically the deformability and the force and the intensity of the forces needed to break a drop. So that means that if you have large values of the Weber number, like the green line, so droplets will break more easily. So we can expect a larger number of smaller droplets and a reduced number of bigger droplets. On the other hand, if you have low Weber number, like the red here, we can expect more larger droplets. And we see that because of this, we see the shift of this peak of a positive work of the surface tension. We have a shift of the peak from small droplets to larger droplets when coalescence is more important, where the average size of the droplet is bigger. We'll get back to this droplet size later on. So now, so far I've worked on, I was working or talking about droplets, but in some sense, I feel that I had to say something also about particles. And now I want to refer to the work here, which this is of Ali, which was defended in March now, who basically did immense boundary method, so simulation of naturally buoyant rigid particles in isotropic homogeneous turbulence. This is visualization. You see this particle, which are relatively small compared to the conventional box. And then we do simulation with varying volume fraction. And we see how the presence of rigid particles will affect the turbulence, the single phase turbulence. A little bit the same, but now instead of having the formable droplets, whose size is not decided, right? The size of the droplet size distribution is basically a result of the simulation. And this will be the rest of the talk basically will be about the droplet size distribution, how we can relate this to turbulence. But now I want to just show what happens in the case of rigid particles. So the size of the particle is fixed. We assume that to be naturally buoyant, so same density. We don't have a gravitational effects or settling. And what we see is basically the same effect. So we have this is the one-dimensional energy spectra. This energy is the Web number. we see as we start with a single phase appear, as we increase the particle volume fraction from 2 to 20%, we see a decrease of the energy at the large scales. At the same time, we have an increase of the energy at the small scales. So we have a similar effect. And with a similar thing, we observe if you do the scale by scale energy budget. Now this is shown in different ways. So we look at cumulative energy fluxes. So what we show here is for the single phase case. So again, the blue is the forcing coming from the F, is the forcing which is needed to sustain turbulence. And we see that, okay, initially there is no energy which has been introduced. So this basically is the integral of the terms we had before. So no energy introduced, and all energy is introduced. And this energy introduced is constant afterwards, right? Because now I introduce all I have to introduce. So I have a constant here because I add 0 basically on every wave number k. This is the dissipation. The green, we see the dissipation just increases with when I move to smaller and smaller scales until it reaches the value of the energy which has been introduced. And the black now here is the effect of the nonlinear terms. This is the energy transferred by the nonlinear terms up to this scale. We see that the energy which is transferred up to each scale is decreasing because what is transported, not all is just going through, because the Reynolds number is not infinite here, so there is also some dissipation, right? So this is the energy transferred by the nonlinear terms, and this decreases because by the dissipation, which is not 0. Now, if I do the same for the case of particles, then I have another term, an additional term, which is the red term here, which is basically the net, the cumulative contribution of due to the presence of the rigid particles. So we can see that, okay, this is now plotted positive, but this is actually with a minus sign. So initially, this will be negative. So this will be energy is removed at a large scale, more and more. Then here I reach a maximum. That means that the energy transfer here is 0. I'm not dissipating more energy at this scale, but I actually have a decrease. That means that I'm now re-injecting energy at the small scales. So this is a way to show basically the same physics, the same trends in terms of fluxes, but now for rigid particle instead of deformable droplets, right? With unknown droplet size, at least initially unknown droplet size distribution. Oops. And now we see for this, we see again the fluxes, we see this is nonlinear terms. As I increase the particle volume fraction, I have a decrease of the importance of the nonlinear term. So now energy is not transferred to smaller scales by nonlinear terms. I mean, it's still transferred, but not as much as before. Part of the transfer now is due to the presence of the particles. And then here we see the effect of the presence of the particles. Here is energy which is dissipated at large scale. And then when I have this decrease, it means that energy now is reinjecting at small scales. But we see that now, unlike the case of droplets, where I know that it's a statistical steady state, I must have 0. I see that when I have a significant particle volume fraction, I don't approach 0. That means that in the case of rigid particle, I have a net dissipation due to the fact that, due to the presence of the rigid particles. Now, let's go back to emulsions, and then let's focus more on what I've just mentioned here and there, but I never really discussed in detail, is basically droplet size distribution, and how can we relate the droplet size distribution to the dynamics of the turbulence flow and vice versa, because it's always unclear what comes first. So this is now the droplet size distribution for the different cases, increasing alpha, changing the viscosity ratio, and also then changing the Weber number. Now, what we observe is that we have clearly these are the same, just this is for changing alpha and this is for changing viscosity ratio. We said we have two ranges, a range at small scale, which goes as d minus 3 halves, and then a range of larger droplet sizes, which is minus 10 divided by 3. And this minus 10 divided by 3 is a scaling which has been traditionally associated to fragmentation processes. So we have a large droplet which may undergo fragmentation, and we have a droplet size distribution, which goes as d to the minus 10/3. And this we can capture quite well when we have the largest volume fraction. And then for small droplets, we see that they follow quite well this minus 3/2 law, which has been observed in experiments. Which is more or less been observed in experiments. Now I want to explain this droplet size distribution and try to see if we can relate this to turbulence. Traditionally, all these theories, or existing theories that we have to discuss droplet size distribution, are based on this Kolmogorov-Hinze theory. So this Kolmogorov-Hinze theory is basically a theory which assumes breakup of droplets in turbulence, and just says that droplets which are large will break because turbulence fluctuation at the scale of the droplet will be large enough to win against the cohesive force due to surface tension, while small droplets will be subjected to lower stresses because of lower turbulence intensity at small scales. So surface tension will be enough to counteract these effects, and droplet will not break. So, and typically what has been assumed is that this transition between these two scalings is associated to the Inscale, so that if I'm above this transition point between the two behaviors, then I have a dominance of breakup, and below I don't have any breakup because the droplets are too small and they can resist deformation by turbulence. So if I follow Hinze reasoning and Kolmogorov, then we can say that okay, the only parameter here is the Weber number, which is basically quantifies the inertia forces over the surface tension forces, where I use the density of the carrier fluid. This is the velocity fluctuations, the intensity fluctuations, and the scale of the droplet diameter, and then I have sigma, the surface tension, where I can use classical Kolmogorov theory to relate the velocity square to dissipation and droplet size. If I now rearrange everything, then I can find the size, dh, the maximum droplet size for which surface tension is able to resist these pressure fluctuations or turbulent fluctuations. Of course, this will be a function of dissipation to the power of minus 2/5 of density of carrier phase surface tension coefficient, but then will also be depend on a critical value of the Weber number, which is basically unknown, and is the object of actually active research, current research. We have this paper by Ruini, for example, last month on national communication, which really focus on the role, on the definition of the critical Weber number, on the role of the vortices which are not of the scale of the droplet size, but are smaller than the droplet diameter. But now to stay with more classical theory, we can just take a result of our simulation, plot using these two non-dimensional groups, as traditionally done, where here we have surface tension and viscosity. Here we have instead we have also the dissipation, and then we have that the relation between these two is these two are related by constant c, where c is the critical Weber number to the power of 3/5. Now, if we use c equal to 1, for example, then we see that more or less we capture the values here that are obtained when changing the Weber number. But if we want to capture the result from the simulation when changing alpha and the viscosity contrast, then we will need to change the value of C from 1 to 2.5. Not that this variation of C will correspond to variation of the Weber number by about 9, because you have this exponent here. And in literature, you can find variation of this of the critical Weber number by more than 100 of magnitude. So this means that, of course, we need to improve this definition. But now what we believe here, what we propose is to use energy flux to define the Inscale. These have results from different simulations, but I can focus maybe on this now. We can see that the crossover between the two scaling, the minus 10/3 characteristic of this large droplet and the minus 3/3 characteristic of the smaller droplets. Now I plot versus K, so wave number K. It can be, the crossover point can be related to the point where the work of the surface tension forces is 0. So that we have on the left, largest droplets, where breakup is expected to dominate, and where we have negative contribution to the kinetic energy budget, scale by scale kinetic energy budget. That means that basically in this region, where breakup is dominant, we have that the energy is absorbed from the turbulence. Then we have the small scale region on the right of this 0, where we have that coalescence is expected to dominate. Coalescence and also, let's say, droplet deformation, droplet relaxation, in the sense that droplet that can be deformed by when interacting with turbulence, but after the deformation, they don't break because surface tension is strong enough, but they will tend to relax to the spherical shape. So we have a region, a small scale, which is dominated by coalescence, in the sense that droplet can coalesce if meeting, but also relaxation in the sense that they can resist deformation and tend towards the spherical shape. In this case, we have this minus 3/2 distribution, and we have a positive contribution. It means that energy now is released to the flow. So this is a picture that we obtain based on statistical analysis and looking at fluxes in the flow. But to get a better understanding, what we have done is to just start from a single droplet and look at the energy fluxes associated with a single droplet in homogeneous isotropic turbulence. We see that as time proceeds, droplet is deforming. And here what I show is the black line is the steady state condition. So that would be the energy flux, the work of the surface tension terms at steady state, and the blue is the instantaneous one. So we can see that with time, we approach the steady state distribution. But let's look more in detail at what happens during the transient. If I start with a spherical droplet, initially I have the droplet deforms and absorbs energy at large scales, initially everywhere, and then a little bit later absorb energy at large scales. So the droplet is there, it starts to deform by the big vortices, and this deformation is associated to a negative work of the surface tension forces, which absorb energy from the flow. Then as the droplet deforms more and more, then of course we have so strong deformation that relaxation and coalescence between the smaller droplet can become important. And then we see that as soon as the deformation is strong and we have smaller structures, we have that the positive part of the spectrum here will become important again. That means that now, as soon as we have the small droplets, the small coalescence of the small droplets, and also the fact that they're so small that they don't break, but they want to come back to the spherical shape, we have this positive contribution. It means that now they start to release energy at small scales. Okay. So this is what the picture we have obtained. And now let's see if we can relate somehow the intermittency of the flow to the droplet size distribution. So basically I have two more things I would like to say. The first one is about the intermittency. So this is the relation I showed before, basically Hinze equation. The critical droplet diameter is a function of this critical Weber number, and then this physical parameters, where epsilon is the turbulent dissipation. Now, because of this, we can expect the probability distribution of the droplet size diameter d and of the dissipation epsilon might be related, because we know that epsilon goes as d to the -5/2. So that means that if we rearrange this, we can write the probability distribution of the dissipation in the flow is equal to d times with the 2 the 13 over 2 times the droplet size distribution. This can be obtained by with this expression where we basically equate the integral of the distribution of epsilon to the integral of the distribution of the droplet sizes multiplied by the volume of each droplet. Using the fact that d goes as epsilon to the minus 2 over 5. So, and this is actually what we want to compare in our simulation from the result of our simulation. We see that the PDF obtained from the droplet size distribution very well matches the one which is actually started from the simulation. Here, the lines, the dashed lines, are the PDF of the dissipation obtained from the droplets. Sorry, is the PDF obtained from the droplet size distribution, and the symbols are the one which actually measure in the simulation. And we see that, especially in this range, we can match very well. And actually, for the case of alpha 0.5, which is the orange, so the binary mixture, we can capture the probability distribution function of the dissipation over all scale, over the entire range. Now, why this works quite well here? Because, of course, this is based on this equation is based on it's valid in the inertial range. Basically, assumes Kolmogorov interpretation turbulence. So if we for this to be true, we would need to have droplets which are in the inertial range. And this, if you remember from the previous plot, is more obvious when we increase the volume fraction alpha. So here we have a small droplets which are well into inertial range. Then this relation is valid, so we can predict nicely the probability distribution of epsilon of dissipation from the droplet size distribution. And this could be interesting because if you do measurements, you can typically extract droplet size distribution. So ND is a quantity calculation, while probability distribution of epsilon is more difficult to measure in general. So we see that we have a good agreement. Also, another thing I want to mention is what I was saying at the beginning about epsilon being more intermittent and being stronger in localized region close to the interface. We see here that the PDF of epsilon, this is a single phase value, and we see that the tails becomes much more evident, much stronger in the case of emulsions. So we see that the intermittency increases a lot in the case of multiphase flows, which is what I was trying to say when I showed the visualization before. Now, to conclude, we have a new definition of this Inscale, which is based on the position where the work of the surface tension is zero. Now, let's see if we can relate this now to the characteristic of the flows. We know that the local dissipation rate, epsilon L, at the relevant scale L, can be written like this using the Kolmogorov 62 theory, so taking into account intermittency. We have the dissipation at scale L goes as UL cubed divided by L, which is basically sigma pi of L, where pi of L is the energy transfer from the nonlinear term to the scale L. So now, if the work of tension is zero at this scale K as zero, then we can associate the energy flux with the local velocity fluctuation at the Inscale. So now we can say that at the Inscale, the local velocity fluctuation are related to the flux in linear terms. So if we use the value of the flux at this point where the work of the surface tension is zero, so if you use the value of the flux at the newly defined Inscale, then we can define the Inscale according to relation. So the Inscale is not this as it was before, but it can be related not to epsilon, which is an average quantity, but we can relate the Inscale to the flux from the linear terms at the scale where the work of surface tension is zero. So at the scale we have this transition from the minus 10 over 3 to the minus 3 over 2 size distribution. If I do this, then I want to compare now from the simulation the estimates of the Inscale So this is the Inscale, where I have these circles, then I have the Inscale as estimated from the classical Hinze law. We see that we have, if we change the green point as before, as we change the surface tension, we more or less follow this line. As soon as we start to change alpha or the viscosity contrast, then we move away from it. But if you now use a new definition, which is based on the contribution of the nonlinear terms at the scale where the surface tension work is 0, then we can see that we more or less follow more closely this straight line, where now this straight line has been modified with the prefactor 0.8. Right? So this straight line, so with this prefactor, we can predict quite well the transition point between the two droplet size distributions, where this prefactor we believe could be due to finite Reynolds number effects. Okay, so let me conclude. I just summarize what I said in this talk, basically divided in two parts. The dispersed phase absorbs energy at large scale and releases energy at small scales. So we have an alternative path for energy transport to small scales, and this was similar to what was observed, for example, in the case of rigid particle, but also with previous work observed in the case of droplets, where droplets were treated with other numerical treatment, for example, from tracking, so that there was no merging and no coalescence. So we have the largest deviation of energy spectra are observed when the dispersed phase has a lower viscosity. But if I want to see the alteration, the most obvious variation on the scale by scale budget, then they are obtained when we change the volume fraction of the dispersed phase, because in that case, you change the total area and then you have more obvious variations. Then we also have seen this extension of the distributive range, which somehow questions a little bit the definition of cosmograph scale in multiphase flows. And that means that we need high resolution if you want to do small scale statistics in multiphase turbulence. Although this doesn't seem to affect too much what happens on the inertial range, as also observed in other studies. So all this work now was published last month on JFM with Marco as a first author. Now let me conclude with what we observed for the droplet size distribution. From the simulation, we could reproduce quite good with a reasonable agreement the -3/2 and -10/3 power laws for the droplet size distribution. Then we could identify the scale separating these two distributions as the zero of the energy transfer due to the surface tension. And this, I think, can provide at least a theoretical definition of Inscale. That could be difficult to measure. Then we have looked at droplet size distribution, and we can see that large droplets are dominated by breakup. And then here we see that energy is absorbed. But also, instead, small droplets are characterized by coalescence and deformation relaxation. In this case, we have a release of energy to small scales in the flow. And then we have what I've tried to show at the end is that this droplet size distribution can be linked to the intermittency that you observe in the turbulent dissipation. Okay, thank you very much. And yeah, I'm ready for questions.
So thank you, Luca, for the very interesting and detailed presentation. So as you said, we can just open the floor for questions. So whoever wants to ask a question, just feel free to unmute your mic and ask the question. You can also write it in the chat. I can report the question if you have any. Okay.
Hello, so maybe I would like so thank you for the presentation. So really, I think it's a really naive question when you mentioned about the droplet size in your study, because at the beginning it's a shape of a sphere, so you can determine the diameter of the sphere, but after that the sphere will be deformed, and how you define as the size of the droplet.
Yeah, okay, then Okay, so as you mentioned, we just start with few droplets with given size, and then we wait. Let's see if I can share again. And then we wait for the droplet size distribution to reach some kind of statistical steady state. Let's see. There's something. We'll just give me a second. Maybe I have to share again, but I need to do like this first. So then once I've run in the simulation, I want to show this movie, then we will see that, yeah, there will be a droplet size distribution we don't know in advance. And then we just we save snapshots of the fields, and then we reconstruct the droplet size distribution during the simulations. So we have time histories of droplet size distribution and total surface area. So the total surface area, as I mentioned, we use to be sure that we are oscillating around the mean value, so we kind of are at steady state. So we trust that we have a statistical steady state. And then, of course, we have this tagging algorithm that is Marco actually used in some previous work. So it's yeah, something he brought with him. I inherited from his previous work, and that we can count the droplet and this according to their size, basically. So we start with something and then we count the droplet according to their size, and yeah, without any reference to shape, in the sense that we just get the volume of each droplet.
Okay. And then maybe just one small question about statistical result of the simulation. So, for example, for one set of parameters, do you perform several simulations to get the statistical result, or you just perform just one simulation?
No, it's one kind of long simulation, let's say.
Okay. So it's in time to.
Yeah. Then we get in time.
Okay.
And then we start to compute the fluxes once we see that the area is not varying in time. And then, of course, this will be quite long because the fluxes are kind of third order statistics, so we need to integrate longer in time.
So in terms of computational cost, how long will it take for the one simulation discard?
I don't know, I think maybe we need 2,000, 4,000 cores for 1 week, 10 days, one case. Yeah.
Great. Okay, thanks.
Thank you.
So is there any someone else who would like to ask a question? Just feel free to unmute your mic and ask the question, or write it in the chat and I can report it. Then maybe I can ask a question myself. Luca, you were showing before the energy budget, like the scale by scale energy budget, and you were showing the difference between single phase and a two-phase energy budget with the energy from that's this one. And then so there is this like the two-phase budget in which you have the surface tension forces which kind of switch sign at a certain point, and then what you said is that basically dissipation kind of extends on a longer range, actually to compensate for the S term. Is it clear how the surface tension transfers? What is the topology of the droplets that transfer the energy at the high wave numbers? Like, is it like more filament-like? Is it more spherical-like? Or is it like, is there something you can tell out of it, or not really?
I don't know, because we looked more in statistical sense, so I'm not sure. I would say that when they're small, they tend to be more spherical because they can resist the formation.
Yeah, but what I was imagining is that basically when they're big enough to break, then you kind of get satellite droplets which are kind of very small and they keep remaining spherical, and then you get filament-like droplet which may be small enough to remain filament because you don't manage to break them, but you still manage to deform them somehow, which may transfer some energy to the flow. And I was not just questioning myself what's
this actually, I don't know. We actually, I know that that's some, yeah, I know that there is some work by Prasad Perlekar in India. They're trying to look at energy budget and this scale budget and try to then transfer it back to physical space. I think they have a theoretical formation for this, but I didn't investigate too much. I think in that case, I think it should be possible to try to relate more the topology to what's happening. Our impression is more that you have a release of energy like this positive term. Once you have this smaller droplet that you deform and then kind of come back to the original shape, or if they kind of collide and coalesce, and so they reduce the interfacial area. I remember now that also Ferrante did some work based on wavelets, where he tries to relate the energy production to the to some location in physical space. And what I remember from that study, could be more actually, is that what they observed more clearly is that this dissipation associated to this big vortices that try to form a large droplet, and then they are quenched by this, because while deforming and breaking big droplets, then they lose energy. This, I think, was analyzed more with this wavelet approach, but I'm not sure what they observe as most cases now.
okay. Okay. And maybe just a follow-up. Here you're using I assume like Fourier spectral methods, right? Because
well, no, for the code we use finite volume and with the both, with this algebraic both. But then we use Fourier, of course, for the analysis. But the code is second order finite volume.
And what is the, I mean, the kind of resolution you can reach when you, I mean, is there like some suggestions you can give for in terms of resolution which should be kept when you have like breakup phenomena or coalescence phenomena? Because I think that's also what you were mentioning when
I mean, of course, inevitably there will be very small droplets that are not well resolved. But yeah,
but I think at a certain point maybe you get like a mass average, like a mass budget, which you can kind of use to identify if you're losing mass or if
no, the mass we don't lose with the both. Basically, the mass is conserved.
It's conserved.
Well, some of the we have more troubles because some of the droplets are too small, and then the interfacial construction is not too accurate. Also because we have this algebraic both.
Yeah.
But that's more. Yeah, I think it's not a problem of mass. It's more like the accuracy of the interfacial forces once they drop it a little bit too small.
Yeah. Yeah, I understand. Okay. So let's see if there is someone else who would like to ask a question. Once again, just feel free to unmute your mic and ask the question, or you can just write in the discussion and I can report it. So that doesn't seem to be the case. Okay, then thank you once again, Luca, for the very interesting talk, and thanks for the detailed seminar. I invite the audience to thank you once again, and Thanks for sharing this very new results.
Thank you.
I wish you a good evening, and hope to see you soon. To see you all next week. Bye.
Bye.